We are starting with an acyclic diene having phenyl group. We are getting a product which is acyclic diene having phenyl group. So, obviously, it is a sigmatropic reaction. Our starting compound is optically active. What will we call the starting material? Where should I number it from, here or here? So, 1,5-heptadiene, 3-phenyl, 3-ethyl, 1,5-heptadiene. We have to specify geometry of double bond. That's say E double bond. We have to specify stereochemistry at carbon number 3. So, carbon number 3, phenyl group is first, this is second, this is third, this stripes clockwise direction, ethyl is below, therefore, that is your 3R, 5E. Okay. We have written it in the chair transition state. Our double bond is E. That's 3R. We are going to break the bond between 1 and 1 dashed and going to make the bond between 3 and 3 dashed. Sorry. One, 2, 3, 4, 5, 6, 7, 8. One 5-octadiene, 3-methyl, 6-phenyl, 1,5-octadiene. Okay. What's the geometry of this double bond? Phenyl is high priority, this is high priority, they are on the same side. So, that is your Z. What's the priority order here? This is carbon with double bond, that's saturated carbon. So, that's your R geometry. So, 3R, 5Z. Chirality at this position is transferred to this position. This is an example of chirality transfer. What's the second product? We said earlier that we can't make both transition state. Chair is preferred over both. Okay. So, flip the chair. Obviously, after flipping the chair, there will be no change in absolute configuration. So, R geometry here, that is also E geometry there. What do we now see? Phenyl and hydrogen. Phenyl and this are on opposite sides. So, that is your E geometry. First, second, third, that is your clockwise direction, but hydrogen is up. So, that is your S geometry. So, one compound is 3R 5Z, the other compound is 3S 5E. What are they? Enantiomers, diastereomers, identical. Diastereomers. One double bond is E, one double bond is Z, they are diastereo. Which is 87%, which is 13%. Yes? Second product is major. Okay, so that is 87%. Why? Because here large substituent is equatorial, here large substituent was axial. So, that is the example that we have. Okay. Oh. So, X is equal to CH2, temperature required 20 degrees. X is equal to oxygen, temperature required 60 degrees. X is equal to sulfur, temperature required 100 degrees. This and this can be easily explained. Carbon-sulfur bond is longer than the carbon-carbon bond. Therefore, in the sulfur compound, there is less strain involved. In the carbon compound, there is more strain involved. It is more difficult to explain the difference between carbon and oxygen. Carbon-oxygen bond is shorter than the carbon-carbon bond. So, that explanation is okay. One of the points here is, of course, you cannot have a chair transition state. Therefore, reaction is proceeding through boat transition state. This is what we had stressed earlier also. If both are possible, chair is preferred over boat. If chair is impossible, reaction goes through boat transition state. Okay. With X is equal to CH2. What is this? Enthalpy of activation. That is entropy of activation. Okay. Why do we need entropy? The two groups must arrange themselves. If I write them like this, they cannot form. So, the two groups have to come in the correct geometry for reaction. Therefore, reaction has an unfavorable entropy of activation. Okay. If X is equal to CH2, CH2, when X is CH2, we are going from 3-membered ring to 7-membered ring. When X is CH2, CH2, you are going from 4-membered ring to 8-membered ring. So, enthalpy of activation 23 kilocalories. Entropy of activation minus 11.7 entropy. Increase in the enthalpy of activation. Why? 3-membered ring is very unstable. 4-membered ring is not that unstable. Okay. If X is equal to 3 CH2s, then your starting material has a 5-membered ring and your product will have 9-membered ring. What happens? There is no reaction. Why? Starting material has now become more stable than the product. Okay. All right. We looked at lots of examples of the Cope rearrangement, which is one of the important examples of 3-3 sigmatropy shift. Okay. We look at our next example, and that's the Claisen rearrangement. Okay. When I heat a mixture of these two compounds, what will happen? That is the product of the Claisen rearrangement. Allyl vinyl ether getting converted to corresponding phenol. What is the importance of this reaction as I have written it now? There is no crossover product. This group does not become joined to phenol and that group does not get joined to the naphthalene. Therefore, reaction is intramolecular. It is not intermolecular. There is no crossover product in this. If the groups were becoming separated as radicals, then this radical would combine with that radical and you would get different products. This group is only attached to the phenol and this group is only attached to the naphthalene. Is there some other interesting thing in this? Why does this migrate only to this position? Why does it not migrate to this position? In phenol, both positions are identical, but in naphthalene they are not. So, why are we not getting this product? If I write naphthalene, that's one resonance form. That's the second resonance form. So there are three possible resonance forms. And in two of them, double bond is between 1 and 2 position. And in only one of them, double bond is between 2 and 3 position. And even out of these three, this is very much more stable. Why is this very much more stable? Here both rings are aromatic. Whereas in this, one ring is aromatic, in that again, only one ring is aromatic. So, reaction always goes to the one position in the naphthalene. Let's look at our next example. We have to suggest a mechanism for this reaction. This is generally referred to as the Claisen rearrangement. Okay. So, what's the first step? The labeled carbon, which was initially sp3 carbon, it has shifted and become sp2 carbon. We have broken the bond between 1 and 1 dashed. We have formed the bond between 3 and 3 dashed. In your normal Claisen rearrangement, next step is loss of this proton. But here, there is no proton at this place. Both the ortho positions are substituted. Therefore, it cannot become aromatic. So, it undergoes second reaction. I simply wrote this, just twisted it like this. Now, this is 1, 2, 3, 4, 5. 1, 5 diene, it is going to undergo Cope rearrangement. Both Claisen and Cope are examples of 3,3 sigmatropic reaction. Okay. At this stage, labeled carbon was sp2. Now, once again, labeled carbon has become sp3 carbon. Now, we have the hydrogen to undergo aromatization. Please note that this step is not a sigmatropic reaction. It is an acid catalyzed reaction. So, first step is a Claisen. It cannot become aromatic because both ortho positions are substituted. So, that intermediate undergoes Cope rearrangement. When it undergoes Cope rearrangement, now there is a suitable hydrogen to become aromatic. Normally, we say ketones are more stable than enols. But here we are converting ketone into enol. Why? Because the enol is going to gain 36 kilocalories of resonance energy. Okay. So, that is your next example. Let us look at our third example. This is the expected product of the Claisen rearrangement. But there is a second product, and that is the product which we are now trying to explain. In the normal Claisen, there is an ethyl group in the product. In the starting material also, there was an ethyl group in the product. But in this abnormal Claisen product, there is no ethyl group in the product. So, that is what we are trying to explain. Okay. So, I wrote normal Claisen product. Okay. We broke the bond between 1 and 1 dashed. We made the bond between 1 and 6. Okay. Sorry, that's the mistake. Sorry. Okay. Instead of bringing it, we are bringing it here. So, we have made cyclopropane ring. Okay. If this goes back again, this here, this here, this here, that's going to give you back again normal product. Pick up the hydrogen from the methyl group, break this. But if instead of doing that, instead of picking up the hydrogen from methyl group, we are picking up the hydrogen from the ethyl group. If I pick up hydrogen from here, I go back into this. But if I pick up hydrogen from here, I now have CH double bond CH CH3. So one carbon has a methyl group, the other carbon has an ethyl group. Of course, this is a minor product, but it's also showing how we can get involvement of this intermediate. Please understand, this intermediate is an unfavorable intermediate, will be formed in small amount. It again goes back into aromatic, it can go back into normal product or pick up proton from here and give you abnormal product. Okay. Let's look at our next example. Generally, when it is asked, what is the Claisen rearrangement? The usual answer is the ortho allyl phenol going to allyl ether of phenol going to ortho allyl phenol. But the Claisen rearrangement was actually discovered in the aliphatic systems. Today, everybody thinks that the Claisen rearrangement only in the aromatic system, but the original Claisen rearrangement was discovered in the aliphatic system. This was the 1912. Very interestingly, Clayton's book says it in the opposite way. He gives the aromatic first and then says later it was applied to aliphatic. Historically, it is very different. It was discovered in the aliphatic systems. It is difficult to prepare these compounds, therefore, all the earlier examples became aromatic. Therefore, people say the Claisen was aromatic, but the actual historical factor is this. Okay. So, what is this? What is this alcohol? This will be crotonic acid. Glutamic acid made into crotyl alcohol. And what is this? This is your propanaldehyde, enol form of propanaldehyde. So that's the reaction that we are doing. Enol ether from propanal and crotyl alcohol. Okay, both double bonds are trans. All right. When we heat it, you get 97% of one product and 3% of the other product. Both compounds are acyclic enols. Okay. So, I am sure you can see we have written chair transition state. Okay. All right. So, this double bond is trans, this double bond is also trans. So that's the aldehyde that you get. So we are going to draw Newman projection looking along this bond. Hydrogen here, methyl group on the left, vinyl group on the right. Hydrogen here, methyl group here, vinyl group on the right hand side. Okay, now we are looking at this position. Hydrogen at the top, methyl group here, aldehyde here. Now I am going to bring both the methyl groups on the same side. When I bring both the methyl groups on the same side, methyl group here, hydrogen here, aldehyde here. What isomer is this? 3O erythro. In erythro, similar group should be on the same side. So if methyl is on the same side, the two hydrogens should have been on the same side. So this is your 3O isomer. All right. So what's the other product that we are going to get? Okay. These two hydrogens trans and these two hydrogens cis. What was this? This was your chair transition state. This is going to be your boat transition state. All right. So, as we said in one of the examples, always the lower face is the one towards you. So, this is the one towards us. Therefore, methyl going here, hydrogen going here, aldehyde going here. On the other one, hydrogen at the top, methyl here, vinyl group here. Bring the methyl groups together. Methyl group here, vinyl group here, hydrogen here. Similar groups are now on the same side. So, your erythro product is coming from boat transition state. Your 3O product is coming from the chair transition state. So, that is your A, that is your B. Okay. Allyl alcohol reacting with vinyl ether. What do we want to prepare? We want to prepare allyl vinyl ether. Okay. So, first step, electron rich double bond attacks mercury. Whenever you write mechanism, what is the caution? This is neutral, this is neutral. So, all intermediates should also be neutral. One positive also should be accompanied by one negative. Okay. So, positive species is being attacked by neutral species. So, there must be one positive charge. Okay. Lose a proton. All right. We lose the proton. We are now looking for okay, let's get it. Wait a minute. Okay. So, we have converted it into allyl vinyl alcohol. So, first step in presence of mercuric acetate, we have prepared allyl vinyl ether. Now, of course, allyl vinyl ether is going to undergo Claisen rearrangement. What is the driving force for this? Carbon-carbon double bond is getting converted to more stable carbon-oxygen double bond. That's the example that we had. Okay. We get cyclic enone. So, our starting material has one ring and two double bonds. Our product has one ring and two double bonds. I am sure everybody can see this is the vinyl ether, this is the allyl vinyl ether. We are going to break the bond between 1 and 1 dashed, make the bond between 3 and 3 dash. Double bond is between 1 and 2, double bond is between 1 dash and 2 dash. Okay. All right. So, that's your 1, 2, 1 dashed, 2 dashed, 3 dashed. One dash, 2 dashed, 3 dashed, 3 dashed, that's your 3, 1 dash, 2 dash, 3 dashed. Sorry. Okay. So 3 has joined to 3 dash has joined to 3. Okay. 3 dashed has joined to 3. 3 is joined to COCH3. Three dashed, 4, 5, 1 dashed, and this is 1 dashed. One, 2, and that's your metal. That's the product, but let me get it correctly. What's the mistake? Okay. 1, 2, 3, 3 dashed. Okay. All right. So that's the product. Vinyl ether, allyl ether. Okay. Let's normally you would expect this substituent to have equatorial geometry. But if it has equatorial geometry, it is not properly aligned to carry out the rearrangement. So it flips over. Can you see that chair transition state? So preferred orientation of substituents will be equatorial. In equatorial geometry, it is not in the correct position to undergo reaction. So we flipped it and made it axial. And we created the corresponding aldehyde. Let's look at alkyl lithium 80 degrees. What will this alkyl lithium do? It will abstract this hydrogen. If you use butyl lithium, product is going to be butane. Butane is a gas, so you created this. Okay. We are going to break the bond between 1 and 1 dashed. 1 second, I think I wrote it. CH2. Okay. All. We are going to break the bond between 1 and 1 dash. What is stabilizing this negative charge? Negative charge is stabilized by resonance in the aromatic. It is also stabilized by inductive effect of oxygen. Okay. So, we are going to break the bond between 1 and 1 dashed. We are going to form the bond between 3 and 2 dashed. So, it is a 3-2 sigmatropic reaction. How many electrons are involved? 2 electrons here, 2 electrons here, 2 electrons in the negative charge. So, it is again a 6 electron system. So, you started with an allyl benzyl ether and you got allyl benzyl alcohol. What is this reaction? This reaction is the Wittig rearrangement. So, there are lots of these rearrangements which are examples of the 2-3 sigmatropic carbon migration. Okay. We look at our last 2 examples. Germachrone, sorry. All right. So, this is a terpenoid compound. Next semester you will hear more about this. Okay. So, monocyclic trinone. Your starting material is monocyclic trinone. I hope you are seeing the direction of the arrow. So, this is the product. From the product, we are trying to find out what is the starting material. This is what we said in the first lecture, that if you know product, you can get starting material, you know starting material, you can get product. Okay. So, that is what we are doing here. I hope you can see that chair transition state. What is the relation between this hydrogen and the methyl? This hydrogen and methyl are trans. What is the relation between this methyl and this hydrogen? This methyl and hydrogen are also trans. So that's your macro. Compound has a 10-membered ring, and the 10-membered ring has both double bonds trans. So that brings us to our last example. Monocyclic with 4 double bonds. 2 separate conjugated dienes. Starting material is monocyclic with 4 double bonds. Product is monocyclic with 4 double bonds. Therefore, it must be sigmatropic. I hope you are seeing this. This double bond is trans. This double bond is also trans. If I make it here, that will be 3,3 sigmatropic reaction. What will happen? Methyl and hydrogen trans. Hydrogen and hydrogen trans. We got 2 trans double bonds, but there is no conjugated system. So, alternative is this. You make a 5,5 sigmatropic carbon migration. hydrogen and hydrogen trans, this hydrogen and this hydrogen trans. This double bond trans, this double bond trans, this double bond trans, this double bond trans. How many membered ring do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So we are not getting 3-3 sigmatropic. What we are getting is a 5-5 sigmatropic reaction. Why 5-5? Why not 3-3? When I do 5-5, I get conjugated, 2 conjugated dienes. When I do 3-3, the ring that I get 1, 2, 3, 4, 5, 6, 7, 8, 9 membered ring. Important thing is in the 5-5, the 2 double bonds are going to be conjugated to each other, both double bonds, whereas in the 3-3, all double bonds are going to be isolated. Therefore, 5-5 is preferred to 3-3. When I do 5-5, how many electrons are involved? 10 electrons are involved. So it's again an example of 4n plus 2. Okay. When we meet next time, we will start looking at our next topic, that is optical rotatory dispersion.